Hello and welcome back. We started discussing projections. The definition is still up here on the slide. So a bounded linear operator on an arbitrary normed linear space is a projection if and only if you apply it twice and it gets you back to the original P. If in addition you are in a Hilbert space and the bounded linear operator here in question is self-adjoint, then you call it an orthogonal projection. There's a few basic properties about orthogonal projections that we need to know, written here in this theorem, two of which we've already proven. That is, if you have a projection, you can form this new thing out of it, 1 minus p. That combination we will encounter lots more in the upcoming sections. Turns out that is also a projection and it commutes with the original p, and their product, their composition is equal to the zero operator. More importantly is that and the range of any projection is closed, and there's this curious identity that the range of p is equal to the kernel of 1 minus p, and there's a sort of complementary one, range of q is equal to the kernel of p. What remains to be seen now, what remains to be proven, is the third one, that kernel and range of a projection are complementary subspaces. So in other words, precisely what's written here that I'm currently underlining in green. So any vector you can write as a sum of something in the kernel and something in the range, and that decomposition is actually unique. Good. So let's do the third part. We have to play around with the decomposition. Good. Finally. So it starts very easy. So x is equal to p of x plus 1 minus p of x, right? So that's an identity for any x in your NLS. This shows that, so remember this one here, this is in the range of p, and this one here, this is in the range of 1 minus p, which is the range of q, and the range of q is the kernel of p, right? That's what we already showed up there. So which shows that that any x in X is a sum of y, which is 1 minus px, which is in the kernel of p, and element z, which is p of x, which is in the range of p. Alright, so first part of that statement that these two guys are complementary subspaces is already done. Now we have to verify that the decomposition is unique, and that happens in the usual fashion, just as we did it when we proved the projection lemma. Moreover, this representation is unique since if you have, well, y1 plus z1 is equal to x is equal to y2 plus z2, with the yi's in the kernel of p, the zi's in the range of p, and remember the range of p is the kernel of q, then you do the standard trickery. You take the y's, say, on one side and the z's on the other side. Then you have z2 minus z1. So now the left-hand side is in the, because kernel is a subspace, it's in the kernel, and the right-hand side, also being a subspace, is in the kernel of q, right? So necessarily I claim, let me write it down and then explain. So necessarily y1 minus y2 equals to z1 minus z2 equals to 0. Why is this? Well, so the kernel of q is this 1 minus p, so that would mean 1 minus p. Let's do it for the z's. z2 minus z1 is equal to 0, but that of course is just saying that z2 minus z1 is equal to p times z2, p acting on z2 minus z1. That you just obtain from this here. Yeah, but then it also says that z2 minus z1 is also in the kernel of p, because it's in the intersection there. Yeah, but that means that this right-hand side here is equal to 0, right? So, and there you have it, z2 minus z1 is equal to 0, and then once this guy is 0, of course the left-hand side is also equal to 0. And that's what's written there. Right, so this completes, which completes our proof. Okay, good. Now, let's get back into the clarification of why we call it the projection lemma. So the last part, so this is 3 of the above theorem asserts that projections are always associated with complementary subspaces, right? As soon as you have a projection, you have a complementary, well, subspace decomposition of your starting normed linear space, right? And turns out this is a two-way street if you are working in a Hilbert space. And provided X is a Hilbert space, and the converse is also true, right? So why is this? And that is coming from the projection lemma, and that's why we call it the projection lemma, because it immediately relates the decomposition of your Hilbert space into the sum of the closed subspace and orthogonal complement thereof. It immediately relates it to a projection. That's why it's called projection lemma. Right, so how to see this? If any x in H can be uniquely written as x is equal to y plus z for y in S and z in the orthogonal complement where S is a closed subspace. And then how do we define the corresponding projection? Well, that's easy. PHS, well, that's why it's called a projection. It just projects on that subspace. So I map my arbitrary element X in the Hilbert space just to that part that lies in S, and that is, after all, Y. Okay. Now I claim this defines not just a projection, but actually an orthogonal projection. An orthogonal projection for okay, so what we have to check a few properties, right? So p squared is equal to p, that would be the first one, that this thing is linear and bounded. But okay, linearity is clear. This comes from the decomposition up there, and also the fact that, well, that it's bounded comes from there, because the norm of y is less than or equal than the norm of y plus the norm of z, which is the relevant norm on the direct sum there, right? And moreover, this p squared equal to p should be clear, because if you apply p of x, then you are in y, and well, and then the next step, because you have the unique decomposition, then of course that y will be mapped to itself, right? So p squared is indeed equal to p, right? Y orthogonal projection, well, here's a little computation. So I have to compute the adjoint and show that it's equal to itself for if x prime is equal to y prime plus z prime with y prime in S, with y prime in S and z prime in the orthogonal complement thereof. Then let's look at inner product px x prime. So what goes on? So p of x is mapped to y, and x prime is y prime plus z prime, right? So y is now an element in S, and y prime is in S, but z prime is in the orthogonal complement. So if you split the inner product into a sum of two inner products, then the second guy will go to 0 because c prime is orthogonal to anything in S, so in particular orthogonal to y. Right, so that's why this is y prime inner product. But now I claim by the same logic this is equal to y px prime. Right? Well, not by the same logic, because of the I haven't used that logic again. I've used the definition of p, right? If you apply the projection to x prime, which is y prime plus z prime, then it will also map it to y prime, which I use here. And now you use the logic. So here you can artificially now introduce that z px prime, and this is because z is again in the orthogonal complement, so it is orthogonal to the vector px prime, which is in S. Right, and there you have it. This is x px prime. And why do you have it? Well, because I managed to move the action of p to the second vector without changing p at all, so p is self-adjoint. All right, good. So what we have just realized is that whenever you're in a Hilbert space, there's a one-to-one correspondence between orthogonal projections and closed subspaces, right? Once you have the closed subspace, the projection lemma will give you the decomposition. Once you have the decomposition, you cook up the projection in the way I just showed you. The other way around is actually easier, because that's the third property of the theorem. Okay, so but if you are no longer in Hilbert spaces, then this correspondence between projections and closed subspaces, it fails in general. However, there are a few special cases, Banach spaces, where it can still work, and here is one that we will need later on. So let X be a Banach space and S a finite dimensional subspace. Okay, then you can complement it. But if this guy is not finite dimensional, then in general, that's not going to work out for you. Then there exists a closed subspace S prime, complementary to S. All right, good. Let's prove this. This will use Hahn-Banach theorem. So first, finite dimensional subspaces have a basis with finitely many elements. Pick one, let Xi be a basis for S. Right, so that would use just knowledge from linear algebra. I'm not touching this knowledge from the Hilbert space on the existence of orthonormal bases. We don't have here an inner product in the Banach space in general, so all that I'm using here is knowledge from linear algebra. Let X be a basis, and maybe you discussed this in linear algebra as well. If not, then I will do an exercise. So there's also the dual space, of course, the finite dimensional spaces, and the dual space has the exact same dimension as your finite dimensional subspace S here, so it has again a basis, and that's the one I'm using here. So the associated dual basis for S star, right? And that guy you can actually gauge uniquely in the following fashion. This is sort of the canonical way, uniquely determined by the constraints Fi evaluated on Xj is, well, 1, 0, 1 when I is equal to j, and 0 when not. Okay, this you can achieve. That's a fact of linear algebra. Maybe I'll put it on an exercise sheet. It's not hard. Okay. Good. Now what we do is we extend. So this is now the Fi's form a basis of the dual space of S. So now what you do is you lift this to something in the dual space of the whole full space X while preserving the properties. Okay, and this is Hahn-Banach. All right. By a corollary to the Hahn-Banach theorem, I will just say by the Hahn-Banach theorem, the lecture notes precisely identify which corollary I mean. By the Hahn-Banach theorem, there exists an extension, of Fi I1n, well, this is in S star 2, call it capital Fi I1n in acting on the whole space, so that the property Fixj is preserved. 1, 0, ij, I different from j. Okay, now define well, the projection. Once we have the projection, then the statement about that complementary thing is clear. So K1n Fkx xk, x any vector, and note that, well, first of all, it's bounded linear. Well, that's clear because it's a linear combination of linear bounded things. Note that P is bounded linear operator with P, if you evaluate it on those basis elements, the way the capital F's are constructed, if you substitute there x with xj, then in the sum you have an Fk's acting on an xj, and that's, most of the time 0, only once it gives you the 1. So P of xj is indeed equal to xj for j from 1 to n. Right? Hence, what this tells you is that P squared is equal to P. Okay? So P is a projection. Well, is that clear? So let's do a little computation maybe up here. I have some space. So if you apply P squared on x, what you have to do is you have to, well, substitute P of x into P. So where does this now appear? Well, by construction, it appears in the argument of Fk. So there's a P of x and then xk. All right. So now if you use the formula for P of x again, you will get two sums, one with k, one with j. But then inside the f of k, there will be an xj, right? And that will give you again this 1 or 0, and then you will realize what you have there is precisely equal to P of x, right? Equivalently, you just, well, use this one line, right? Because after all, that P of x is a linear combination of these xj's or xk's. Right? So P is a projection, and what is the range of P? Well, the range of P, so everything that comes out here, remember capital Fk is a linear functional, so that spits out a scalar. So everything here in the range is just a linear combination of the xk's, right? But the xk's are a basis, a spanning set for, what did I call it, S, right? Yeah, that subspace S. So that means simply that the range of P is equal to S, right? And here, hence, thus, the sought after complementary subspace is, well, S prime. So we use that theorem about projections, which is just a kernel of P. See the last theorem. Okay, and we're done. That's it. Very nice. Good, excellent. So that closes this section, and now comes a bigger one, a longer one, about the, well, spectrum. So this will introduce the basic notions of the spectral theory for bounded linear operators, and we will have examples and, well, basic results. All right, so thinking back a little bit to linear algebra, so you can well, think about matrices. That's as good as what I'm doing there. So if you have a linear operator on a finite dimensional space, think of an n by n matrix. After all, they're represented by such matrices. And then you know what eigenvalues are. So eigenvalues, lambda, well, here apparently in C, well, it doesn't have to be C, it could be F. Eigenvalues lambda in F, those are precisely your zeros of the determinant, lambda I minus t equal to 0, right? And so there's a result in linear algebra that the determinant of a linear operator or of a matrix is 0 precisely when the matrix or the operator is not invertible, right? Now, having here this connection to the determinant. Now, the determinant, this is the characteristic polynomial. That's what it's called. So it's a polynomial, and it has at most n roots, which is the dimension of the coordinate space here. It might have, you know, not precisely n roots, because if the field is the real number field, you might not get precisely n, you might get 0. That can happen. It doesn't happen, of course, if you're in the complex number field situation. But anyways, you got eigenvalues. And as I already said, if lambda is not an eigenvalue, that means the determinant is different from 0, then the operator is invertible, or the matrix lambda I minus t is invertible. Okay, and the curious thing about linear algebra is that this is if and only if. Okay, so as it turns out now in infinite dimensions there's much more besides eigenvalues, and that makes the study of the spectrum, whatever that is, we will define it soon enough, much more interesting. Okay, we begin with a few algebraic properties that are also discussed in linear algebra. So this has nothing to do here with the dimension. Let T be a normal operator. So that's the guy that commutes with its adjoint on a Hilbert space H. Yeah, so for the adjoint we need a Hilbert space H. Either over the real or complex number field, and suppose Tx is equal to lambda x for some lambda in F, x in H. Alright, so in linear algebra this is what you would call an eigenvalue, eigenvector pair, but here at this point we don't know. We don't have that terminology yet. Okay, so I won't use it here. I will just write out the claim. Then the adjoint satisfies the same equation except for the fact that the lambda gets a complex conjugate bar on top. Okay. Proof. For all x in H, lambda in F on the next page. Let's look at t minus lambda I x norm squared. Yeah, okay. So that's the norm induced by the inner product. So this is t minus lambda I x, t minus lambda I x. Now remember the adjoint is a conjugate linear isometric isomorphism. So when you move this guy, the whole thing here, not that far, you move it, this one here, then you have to put star outside. There I haven't used yet that conjugate linear isometric isomorphism property, but now I have, so t star minus, and then gets a lambda bar on top because conjugate linear. And then the adjoint of the identity is the identity. So you have this. Okay. So now you carry out the algebra, and using that little check I will leave to you. You just have to multiply out these two brackets. This is exactly the same as t minus lambda I, t star minus lambda bar I acting on x. So you can, in other words, swap the order of the factors there, but that uses normality. Okay, that green equation, do check it. And then what you have is, well, you go backwards, so you go here, not outside, just in front of the x, inside the inner product, here. Well, and then you have, let's shorten this a bit, lambda I bar x norm squared, right? So, in other words, hence tx is equal to lambda x, that makes the left-hand side equal to 0, happens precisely. So actually we proved more than what was written up in the statement, if and only if, well, t star x is equal to lambda bar x. Well, no, I shouldn't say we proved more, because the initial, my statement up there was valid for any bounded linear operator, so you could just replace t by t star, and then you get that if and only if there. All right, that's it. That's that statement. Maybe I will just write the next one, but I will prove it in the next video. This is also known if t is normal operator, and x, y, okay, let's write it then, is a normal operator. Operator on a Hilbert space H, and x, y in H, lambda mu in F, such that tx is equal to lambda x and t mu, not mu, ty, y is equal to mu y with lambda different from mu, then the vectors x and y are orthogonal. Okay, this is known probably from linear algebra. This is the statement that eigenvectors of normal operators corresponding to distinct eigenvalues are orthogonal. Okay, but here again I'm not using this language, since I haven't defined yet what are eigenvalues and eigenvectors for operators on infinite dimensional Hilbert spaces. This will come, however, soon enough, and then we will build up very nice theory and discuss many examples. I'll see you soon.